Welcome back, everybody, for another deep dive. This time, we're going to be talking about electromagnetism.
Ooh, exciting.
Yeah, but, not the theoretical physics kind. We're going very practical with this one.
Okay.
We're going to be looking at how electromagnetism is actually used out there in the world in industrial processes,
Very cool.
based on some pretty technical sources you've brought. So buckle up. We're going to cover a lot of ground here.
All right. Sounds good.
We're talking everything from induction heating to the nuances of coil windings in motors, even some really surprising applications,
Oh, I like surprising applications.
like using electromagnetism to shape metal
Ooh.
or even weld plastics together.
Really? I didn't know you could do that.
Yeah, so it's going to be a wild ride.
All right, I'm ready. Let's go.
Okay, so let's start with electromagnetic induction heating. Can you give us just like a basic rundown of how that even works?
Sure. Yeah. So electromagnetic induction heating, it works by using a fluctuating magnetic field to basically create electric currents within a conductor.
Okay.
And these currents generate heat within the material itself. So it's kind of a hands-off heating method.
So there's no like direct contact.
Right. It's a contactless process.
Okay.
And that's one of the big advantages, because it means you can actually heat materials, sensitive materials, that you wouldn't want to directly touch
That makes sense.
without, damaging them.
Right. And I see from examinempty1.pdf, there's some serious advantages to this method.
Yeah.
What really jumped out at you?
The speed and efficiency is really impressive. Like, this method can heat materials much faster than traditional methods. And that, of course, leads to significant energy savings, which is always good.
Yeah, absolutely.
The source actually mentions a reduction in material loss due to oxidation as well,
Oh, wow.
which can be a huge cost saver in industrial settings.
So it's faster, more efficient, and cleaner. That's pretty amazing. Are there any downsides? Anything we got to watch out for?
Well, the source does mention that it requires specialized power sources, which can be expensive to install and maintain.
Okay, yeah, that makes sense, right? There's always a trade-off somewhere.
Right.
But I guess for applications where precision and control are essential, it seems like it'd be a total game changer.
Sure. Yeah.
The source mentions melting metals and heat-treating parts as some of the examples. What kind of parts are we talking about?
So we're talking about, hardening gears for increased durability and annealing metal to make it more workable. It's used extensively in the automotive and aerospace industries,
Cool.
like hardening the surface of a car crankshaft
Okay.
for improved wear resistance.
So next time I see a car commercial boasting about their durability, I'll know that there's some clever electromagnetism at play.
Exactly.
All right, let's shift gears to something that sounds like it's straight out of science fiction: plasma processing.
It does have a certain futuristic ring to it.
It does.
Yeah. So plasma processing uses extremely high temperature plasma to cut and process materials.
So we're talking temperatures hot enough to slice through metal like butter.
Pretty much, yeah.
Okay, so why use plasma instead of more conventional tools? What's the advantage there?
So it's particularly useful for materials that have really high melting points
Okay,
that are really difficult to manipulate with conventional methods.
gotcha. The source mentions two types of plasma generators: arc plasma and plasma jet. What's the difference between those two?
So arc plasma generators create plasma using an electric arc between two electrodes, while plasma jet generators use a high-velocity gas flow to generate the plasma.
Okay.
The choice depends on the application and the material being processed. For example, arc plasma is often used for cutting really thick materials,
Okay.
whereas plasma jet is more suited for precise cutting and surface treatment.
So it's about choosing the right tool for the job based on the material and what you're trying to achieve.
Exactly.
Okay, that makes a lot of sense. All right, let's move on to something a little closer to home, I think. High frequency and microwave applications.
Right.
So we all know about microwaving our food, but I have a feeling there's a lot more to this story.
You're absolutely right. High frequency and microwave applications, they rely on the principle that these electromagnetic waves can directly heat certain materials.
Okay.
We call these dielectric materials.
Okay.
And this basically allows for selective heating based on the material's properties.
Oh, that's why the plate doesn't get hot when I microwave my leftovers.
Exactly. That's
Like-
the same principle.
The source mentions drying textiles and paper and even glue as some industrial applications.
Yeah,
It's crazy how versatile this technology is.
it really is. Yeah. And the applications go way beyond just heating things up. Microwaves are used in industrial settings for sterilizing pharmaceuticals, vulcanizing rubber, even assisting in certain manufacturing processes.
Wow.
It all comes down to, harnessing the power of electromagnetic waves to achieve a specific outcome.
It makes you wonder what other applications are just waiting to be discovered.
Yeah, exactly. Who knows what the future holds?
Right. Speaking of discoveries, let's dive into the world of joining and welding technologies.
Oh, yes.
This is where we see electromagnetism being used to create really strong, reliable bonds between materials. The source covers a range of techniques from something called wedge bonding, which sounds pretty straightforward to me.
It is, yeah.
To the much more, complex process of welding.
Right.
So can you just give us a quick overview of wedge bonding?
Sure. So imagine inserting a wedge-shaped piece of metal into a corresponding slot.
Okay.
That simple action creates a very secure mechanical bond.
Okay.
And it's often used for applications where you might need to disassemble the components later.
Right.
Like attaching a fan to a motor shaft or something like that.
Okay, that makes sense. But for permanent connections, you'd want something more robust, like welding. The source goes into some pretty specific parameters that influence the welding process. What are some of the key factors to consider?
Yeah, the source highlights current intensity, arc voltage, welding speed, and arc length as being really crucial parameters in welding.
Okay.
Controlling these factors really precisely is key to achieving a strong, reliable weld. It's a very delicate balance, and even slight variations can affect the quality of the weld.
I'm starting to get a sense of the complexity here. The source specifically mentions tungsten inert gas welding or WIG welding.
Yes.
What makes this method unique?
So, WIG welding uses a non-consumable tungsten electrode to create the arc,
Okay.
and an inert gas, usually argon, to shield the weld pool from atmospheric contamination.
Oh, okay.
And this results in a very high-quality weld with minimal spatter and excellent penetration.
So it's a cleaner, more precise welding method. What kind of applications would you use that for?
It's often used for welding thin materials and dissimilar metals where precision and control are absolutely critical.
Okay.
So, think delicate components in aerospace applications or joining different types of metals in a high-performance engine.
Got it. So we've got WIG welding for precision work, but what about high-volume manufacturing, like, building cars? The source mentions spot welding for that.
Yes, spot welding is a really efficient method for joining sheet metal. It uses a pair of electrodes to apply pressure and heat to a localized area, creating a weld nugget that joins the materials together.
Okay.
And it's really quick, it's reliable, it's perfect for, like car assembly lines where speed and consistency are paramount.
So it's fascinating how each welding technique has its own strengths and weaknesses.
It is, yeah.
And choosing the right one depends on the specific application.
Absolutely.
But all this talk about joining metals makes me wonder about the materials themselves. I'm guessing not all metals are created equal when it comes to electrical applications.
That's a great point, and you are absolutely right. Selecting the right material is so crucial in electrical engineering.
Yeah.
Because each material has unique properties that affect its performance.
Okay, let's unpack that. I'm really interested to learn more about, the different types of materials that are used in electrical engineering and what makes them suitable for specific tasks.
Excellent. Well, let's start with magnetic materials, which are essential for devices like transformers and motors.
Perfect. Let's dive in. Okay, so magnetic materials, like the stuff that makes motors and transformers, hum.
Exactly, yeah.
What are some of the key things to consider when you're choosing a magnetic material for a specific application?
Well, one of the most important factors is energy loss.
Okay.
You see, when you magnetize and demagnetize a material, some energy is inevitably lost as heat.
Right.
And this is due to a couple main factors, something called hysteresis and eddy currents.
Okay, break those down for me. What are hysteresis and eddy currents, and why should I care about them?
Okay, so hysteresis loss is basically related to the energy that's needed to realign the magnetic domains within a material. So you can kind of imagine like trying to turn a rusty gear. It takes more effort because of that friction. Similarly, some materials resist changes in their magnetic state. And that leads to these energy losses.
So some materials are easier to magnetize and demagnetize than others.
Exactly, yeah. And that's where the concept of soft and hard magnetic materials comes in.
Okay, I'm intrigued. What makes a material magnetically soft or hard?
So soft magnetic materials are really easy to magnetize and demagnetize.
Okay.
They respond really quickly to changes in magnetic fields.
Okay.
And this makes them ideal for applications like transformers, where the magnetic field needs to switch direction rapidly.
Gotcha. So hard magnetic materials, they're like the opposite.
Exactly. They're really difficult to magnetize.
Okay.
But once they are magnetized, they retain their magnetism very well. Think about the magnets you stick on your fridge. Those are hard magnetic materials.
Okay, so soft magnetic materials are for dynamic applications.
Yeah.
And hard magnetic materials are for, permanent magnets. Okay, that makes sense. Now, you mentioned eddy currents as another source of energy loss. What are those?
So eddy currents are basically circulating currents that are induced within a conductor when it's exposed to a changing magnetic field.
Okay.
You can kind of think of them like swirling eddies of water in a river. They create their own magnetic fields that oppose the main field. And this leads to energy losses as heat.
So we want to minimize both hysteresis and eddy current losses to make our devices as efficient as possible.
Exactly, yeah. And that's where, clever material selection and design come into play.
Right.
Like, you mentioned silicon steel sheets earlier. Those are specifically engineered to reduce energy losses in transformers.
Right. You said that adding silicon to steel increases its resistivity, which helps reduce those eddy current losses. But how much of a difference does it actually make in practice?
Adding even just a small amount of silicon can really significantly reduce those energy losses.
What?
In fact, modern transformers using silicon steel sheets are about 98% efficient.
Wow.
Meaning that only about 2% of the energy is lost as heat.
That's incredible. It's amazing how such a small change in material composition can have such a big impact on efficiency. What about those other magnetic materials you mentioned, like amorphous metal and ferrites? Where do those fit in?
Yeah, so amorphous metals, these are really fascinating. They have a kind of disordered glass-like structure, and this gives them very low hysteresis losses and high permeability, which makes them really ideal for high-efficiency transformers and sensors.
So they're like the super efficient magnets. Are they used very much out in the real world?
They're, still relatively new.
Okay.
And more expensive to produce than the traditional silicon steel, but they're definitely gaining popularity as efficiency demands continue to increase.
It sounds like we're on the cusp of like a new era of magnetic materials. You also mentioned ferrites. What makes them unique?
So ferrites are ceramic materials with magnetic properties. What's really interesting about them is that they're electrical insulators.
Whoa, okay.
Which means they don't actually experience those eddy current losses.
Right.
So this makes them ideal for high-frequency applications like inductors and transformers used in, radio communications and electronic circuits.
So it's a whole different set of properties and applications compared to the metals.
Right.
It's amazing how diverse the world of magnetic materials is.
It really is, yeah.
But let's not forget about the other half of the equation, the conductors. Those are the pathways for the electricity to actually flow through, right?
Exactly, yeah. Without good conductors, all that work we put into optimizing magnetic materials would be kind of wasted.
What makes a good conductor anyway? I know copper is like the popular choice, but what makes it so special?
Yeah, so copper is an excellent conductor because it has very low resistivity, meaning that electricity can flow through it very easily with minimal energy loss.
So it's like a superhighway for electrons.
You got it.
Are there other materials that are good conductors?
Yeah, so aluminum is another common conductor. It's not quite as conductive as copper.
Okay.
But it is lighter and less expensive. So it's a good choice for applications where, weight and cost are important considerations.
I see. So it's a trade-off between conductivity and, cost and other factors.
Right.
We were talking about coil windings earlier. Those are, lengths of conductive wire wound into specific shapes to create magnetic fields. I'm curious, what kind of conductors are typically used for coil windings?
So copper and aluminum are actually the most common choices for those coil windings for the same reasons we just discussed.
Right.
The choice really depends on the specific application and factors like, cost, efficiency, operating temperature, that kind of thing.
Okay, that makes sense. But I'm guessing there's more to coil windings than just choosing the right conductor.
Right. You're absolutely right.
Okay.
The shape and the arrangement of the windings are also super crucial for optimizing the performance.
All right, we talked about like different types of windings, cylindrical, spiral, layered, in buckets, I think was one of them.
Yeah.
I can remember the different shapes, but can you remind me, why does the shape actually matter so much?
Yeah, so the shape of the winding affects its inductance, which is basically a measure of its ability to store magnetic energy.
Okay.
It also influences the distribution of the magnetic field, which is crucial for how the device actually works. For example, in a motor, the shape of the windings actually determines the strength and direction of the magnetic forces that make that rotor spin.
So it's not just about cramming as much wire into a small space as possible. It's about carefully designing that winding to achieve the desired magnetic field.
You got it. It's all about precision and control.
Yeah.
And another critical factor is insulation.
Right. We don't want all those wires, touching each other, creating short circuits. What kind of materials are used to insulate those coil windings?
So, a variety of materials can be used. It really depends on things like the voltage, the temperature, and the mechanical stress that the winding is going to be subjected to. Enamel coatings, paper wraps, even textile fibers like cotton and silk have been used historically.
Oh, wow.
Modern windings often use synthetic polymers for their excellent insulating properties and durability.
So there's a whole science to choosing the right insulation for the job. You also mentioned a process called impregnation, where the winding is coated with like a varnish or a resin. Why is that step necessary?
Yeah, so impregnation actually serves a few purposes. First, it fills in any air gaps.
Okay.
It might exist between the wires and the insulation layers. And this improves heat dissipation, which helps to prevent the winding from overheating. Second, it creates a protective barrier that prevents moisture and contaminants from getting into the winding, which can degrade its performance over time.
Uh-huh.
And third, it actually adds mechanical strength, helping to hold that winding together and resist vibration and stress.
So it's like giving that winding a suit of armor to protect it from the elements and keep it running smoothly. Are there different types of impregnation materials?
Yes, there are. The choice depends on, factors like the operating temperature, the required level of protection, and compatibility with the other winding materials.
Yeah.
Some common choices include epoxy resins, polyester resins, and varnishes that are based on, natural or synthetic polymers.
Okay, so there's a whole art and science to selecting the right materials and processes for these coil windings. It's a lot more complex than I initially thought. But what about the other end of the motor? The rotor. We were talking about squirrel cage rotors earlier. I'm still a little fuzzy on how those actually work.
Sure. So a squirrel cage rotor is actually a pretty fascinating piece of engineering. It consists of a series of conductive bars that are embedded in a laminated iron core.
Right.
And they form this structure that, as the name suggests, kind of resembles a squirrel cage.
Right. I remember the squirrel cage analogy, but how does that structure actually make the motor spin?
So it's all about electromagnetic induction.
Okay.
When a rotating magnetic field is applied to the stator, that's the stationary part of the motor.
Right.
It induces currents in those rotor bars.
Yeah.
And these currents create their own magnetic fields that interact with the stator field, producing a torque that makes the rotor spin.
So it's like this constant push and pull between the stator and the rotor magnetic fields, making the motor turn. What are those rotor bars typically made of?
So aluminum is actually a popular choice for the rotor bars because it's lightweight, it's got good conductivity. But copper and other alloys are also used, depending on the motor's requirements.
And the source mentioned different types of squirrel cage rotors, right? What are the key differences?
Yeah, the main distinction is in how those rotor bars are attached to the end rings.
Okay.
So in a welded rotor, the bars are individually welded to those end rings. Mm-hmm. And this creates a really robust structure.
Okay.
But it can be more expensive to manufacture. In a cast rotor, the bars and end rings are actually formed in a single casting process, which is much more efficient. Mm-hmm. But it does require very precise control over those casting parameters.
So it's a trade-off between manufacturing cost and structural integrity. What factors determine which type of rotor is best for a particular application?
So the choice really depends on things like the motor's power rating, the operating speed, and the required starting torque. So, welded rotors are generally preferred for those high-power motors where, robustness is absolutely critical.
Okay.
While cast rotors are more common in lower-power applications.
Right.
Where cost is a major consideration.
It's amazing how every detail, from the material composition to the manufacturing process, can affect the performance of these components.
It really is, yeah.
It's like a finely tuned orchestra where every instrument needs to be in perfect harmony.
That's a great analogy. And speaking of harmony, let's not forget about the importance of testing and quality control.
Right.
To make sure that all these carefully designed components actually work together seamlessly and reliably.
We talked about various tests, like resistance measurements, insulation resistance tests, high voltage testing. What are some other tests that engineers use to ensure the quality and reliability of these electrical components?
Oh, there's a whole suite of tests designed to evaluate, very specific aspects of a component's performance. For example, there are tests to measure the magnetic properties of materials, like, permeability and coercivity. There's also tests to assess the mechanical strength of the windings and rotors, making sure they can withstand the stresses of operation. And then there are specialized tests to evaluate the performance of components under, very specific environmental conditions, like high temperatures, humidity, or vibration.
It's reassuring to know that so much effort goes into ensuring the quality and reliability of these components. But all this talk of, testing and materials makes me wonder, what's on the horizon for electrical engineering? Are there any exciting new technologies or materials that are poised to kind of revolutionize the field?
That is a great question. There's a lot of really exciting research happening right now in areas like nanotechnology, superconductivity, and even bio-inspired materials.
Okay, now you've got me really intrigued. Can you give us a glimpse into what these cutting-edge technologies might hold for the future of, our electrical devices?
So imagine conductors that carry electricity with zero resistance, or motors and generators that operate with unprecedented efficiency. That's the promise of superconductivity.
Wow.
And the nanotechnology is opening up a whole new world of possibilities for creating materials with tailored properties.
Mm-hmm.
This could lead to more compact, more efficient, and more powerful devices.
It sounds like we're on the verge of like a technological leap forward.
It really does feel that way.
Yeah. But before we get too carried away with the future, let's take a closer look at some of the, fundamental principles that underpin all these advancements. For example, you mentioned energy losses earlier. I'm curious, what are some of the ways that engineers try to actually minimize those losses in real-world applications?
That's a great question. There are a number of strategies that engineers employ to, combat those energy losses.
Let's delve into those strategies in part 3. Join us as we explore the clever techniques that engineers use to squeeze every last bit of performance out of our electrical devices. All right, so we're back, and we've been on this awesome journey exploring electromagnetism and all its applications, from melting metal to spinning those motors. And before the break, we were talking about energy losses, that reality that some energy is always lost as heat.
Right, it's inevitable. You can't get away from it.
So how do engineers try to minimize those losses and make our electrical devices as efficient as possible?
Yeah, well, they've got a whole bunch of tricks up their sleeves. One common approach is using materials that have those, low hysteresis and eddy current losses that we were talking about earlier.
Right.
Like silica steel sheets, amorphous metals, ferrites. They're all, great examples of materials that are specifically engineered to reduce those losses.
So it's about choosing the right materials for the job. Are there other tricks that they use, though?
Oh, absolutely. Another approach is to optimize the design of the actual components themselves to minimize that energy loss.
Okay.
For example, in transformers, using laminated cores, which are thin sheets of magnetic material stacked together, can help reduce those eddy current losses.
Why does that work?
So eddy currents actually flow in loops.
Okay.
And breaking up that core into those thin sheets basically limits the size of those loops.
Uh-huh.
So it's kind of like dividing a wide river into, narrower channels. The water flows more smoothly and with less turbulence.
That's a great analogy. So clever design can go a long way in improving that efficiency. Are there any other design tricks that they use?
Yeah. Another common technique is to reduce the operating frequency of the device.
Okay.
Remember, eddy's current losses are proportional to the square of that frequency.
Right.
So lowering the frequency can really significantly reduce those losses. Of course, this isn't always possible. Some applications require those high frequencies.
Yeah, you got to strike a balance, right?
Exactly. It's always a trade-off.
Between, performance and efficiency. What about things like cooling systems? Do they play a role in managing those energy losses?
Of course, yeah. Effective cooling is essential for dissipating the heat that's generated by those energy losses, to prevent the device from overheating.
Right.
And this might involve, using heat sinks, fans, or even liquid cooling systems.
Yeah.
Depending on the application.
It's crazy how much engineering goes into managing, something as seemingly simple as heat.
It really is.
Yeah. It really highlights like how interconnected all these different aspects of electrical design are.
Right.
We've talked a lot about, individual components like transformers and motors, but how do these components actually fit together in, those larger electrical systems?
So that's where the field of power electronics comes in.
Okay.
Power electronics basically deals with the control and conversion of electrical energy in various applications. It's really the bridge between that, electrical grid and the devices that we all use every day.
So power electronics is important.
It's essential, yeah.
Can you give me like an example of how power electronics is used in real life?
Sure. So think about like a laptop charger.
Okay.
It uses power electronics to convert that AC voltage from the wall outlet to that DC voltage. That's needed to charge the laptop battery. It seems like a simple device.
Right.
But it involves, some pretty sophisticated circuitry.
Yeah.
To regulate that voltage and current very precisely.
So power electronics is kind of like a translator between different types of electrical energy.
That's a good way to think about it.
Yeah.
And it plays a really vital role in a ton of different applications, from, renewable energy systems to electric vehicles.
Sounds like a rapidly evolving field.
It really is, yeah.
Are there any, exciting new developments in power electronics that, we should be aware of?
So one exciting area is the development of wide bandgap semiconductors like silicon carbide and gallium nitride.
Okay.
These materials can actually handle much higher voltages and temperatures than traditional silicon semiconductors, leading to more efficient and compact power electronic devices.
So it's like upgrading the infrastructure of the electrical world.
Exactly.
Yeah.
And these advancements are really enabling the development of more efficient electric vehicles, faster charging systems, even more powerful renewable energy systems.
That's fantastic. It's incredible to think about how all these seemingly like disparate pieces from, the properties of those materials to the design of the components to the control of electrical energy all kind of come together to shape our technological world.
It really is amazing. It's a real testament to human ingenuity.
Yeah.
Our constant pursuit of understanding and harnessing the power of electromagnetism.
Well, I gotta say, this deep dive has been truly electrifying. We've covered so much ground, from the fundamental principles of electromagnetism to the very intricate details of materials, components, and systems.
Yeah, it's been a really fascinating journey for me, too. It's a good reminder that even those, commonplace devices that we all use every day are really marvels of engineering.
Yeah.
Built upon a foundation of scientific understanding and technological innovation.
I think I can speak for both of us when I say we've only just scratched the surface of this vast and ever-evolving field.
Absolutely. There's always more to learn and discover. And as technology continues to advance, the possibilities for harnessing electromagnetism are, really limitless.
That's a great note to end on. Thank you so much for joining us on this electrifying exploration of electromagnetism. We hope you've gained a deeper appreciation for those, invisible forces that shape our world and the ingenious ways that we've learned to harness them.
It's been a pleasure to be here.
Until next time, keep those sparks of curiosity flying.